High above the Northern Hemisphere, a river of wind that normally circles the entire planet in a matter of days has stopped moving. Forecasters are calling it a blocking pattern, and right now it is anchored directly over the northern reaches of Europe and North America, refusing to budge while entire weather systems pile up behind it like traffic stuck behind a closed road. To understand why a stalled wind current thousands of feet above your head actually matters, you first need to understand what the jet stream normally does for the planet. Picture a fast-moving band of wind circling the globe west to east, acting as the boundary line between cold Arctic air to the north and warmer air sitting to the south. Under normal conditions, this river of the wind keeps weather systems moving along briskly. Hot meaning a rainstorm, a heat wave, or a cold snap typically passes through a region within a matter of days before the jet stream pushes the next system in behind it. This constant motion is actually the reason most weather feels manageable in a typical year. A heat wave that might otherwise linger for weeks gets nudged along by the next low. Pressure system riding in behind it, bringing clouds, cooler air, or rain that resets the pattern before conditions become truly extreme. The jet stream functions almost like a conveyor belt for weather itself, cycling through highs and lows in a predictable rhythm that farmers, city planners, and emergency services have built entire systems of preparation around for generations. Blocking flips that entire process on its head. Professor Tim Willings, a physical climate scientist at the University of Oxford who has written extensively on jet stream behavior, describes blocking as a stationary and persistent weather pattern, most often a high-pressure system, that physically blocks the oncoming jet stream and the storms riding along with it. Instead of weather moving, through in days, a blocked pattern can trap conditions in place for weeks at a time, turning what should be a passing weather event into a prolonged, grinding ordeal for anyone living underneath it. Think of it like a boulder dropped into the middle of a fast-flowing river. Water does not simply stop moving when it hits that obstruction. It backs up behind it, pools, and finds itself forced into a completely different path than it would have taken otherwise. A blocking high-pressure system does something remarkably similar to the atmosphere. Instead of the usual parade of weather systems marching steadily eastward, everything backs up behind the block, forcing storms and fronts to detour around it, while the region directly underneath the high-pressure system gets stuck with whatever conditions that block happens to bring day after day after day. This is not some rare, once-in-a-generation atmospheric quirk either. Blocking events have been directly linked to some of the most notorious extreme weather disasters in recent memory, including the brutal heat and drought that gripped the UK during the summer of 1976 and the deadly European heat waves that followed in later decades. When a high-pressure block settles in during summer, the result is typically clear skies, no rain, and steadily climbing temperatures day after day, with nothing arriving to break the pattern. The same mechanism works in reverse during winter, which is part of why blocking gets so much attention from meteorologists year-round, rather than only during heat season. A blocking high-pressure system parked in exactly the wrong spot during winter can just as easily trap frigid Arctic air over a region for weeks, producing the kind of prolonged, bitter cold snaps that catch entire cities off guard, straining power grids and water systems never designed to handle sustained deep freeze conditions. Whether it traps heat or cold, the underlying atmospheric behavior driving both scenarios is fundamentally the same stalled, stuck pattern. So what is actually setting up this particular block right now, and why is it forming with this much force? Forecasters tracking the current pattern point to an unusually powerful El Nino event as one of the primary drivers. Meteorological analysts describe the pattern shift emerging over Europe as one of the clearest signals yet of a super El Nino locking down atmospheric circulation, with a blocking high anomaly building over the northern and north-central regions of the continent, paired with a tendency toward low pressure further south. Here is the mechanism behind that connection, laid out simply. El Nino works by redistributing enormous amounts of ocean heat across the tropical Pacific, and that redistribution ripples outward into the broader atmosphere, reshaping pressure patterns far beyond the ocean itself. Forecasters analyzing the current pattern say this sign Al has already started emerging in rainfall projections for the rest of July, with below normal rainfall expected across the central United States, the northern plains, the upper Midwest, and the Pacific Northwest, while regions like the Southwest and parts of the northeastern United States and Canada see the opposite effect, with more rainfall than usual. That kind of reshaping happens because the tropical Pacific plays an outsized role in steering global atmospheric circulation, functioning almost like a thermostat for weather patterns thousands of miles away. When ocean temperatures shift as dramatically as they do during a powerful El Nino event, the atmosphere above responds by adjusting where its major high and low pressure systems tend to sit, and those adjustments cascade outward across entire hemispheres. This is precisely why forecasters watching a strengthening El Nino this year are paying such close attention to blocking signals showing up not just in the Pacific, but thousands of miles away over Europe and North America as well. If you are finding this explanation genuinely useful, take a second and hit that like button right now. It helps this channel keep bringing you research-backed breakdowns like this one straight from the atmospheric science itself. But El Nino is not the only force scientists believe is reshaping how often and how powerfully these blocks form. There is a second, slower moving factor at work, one tied directly to how quickly the Arctic itself is changing. The Arctic Council has highlighted research showing that the Arctic is now warming roughly 3 times faster than the global average, and that accelerated warming is quietly reshaping the entire structure of the jet stream itself. Here is why that temperature gap matters so much. The jet stream exists specifically because of the temperature difference between the cold Arctic and the warmer air further south, and the strength of that temperature contrast is what determines how fast and how straight the jet stream flows. As the Arctic warms faster than the rest of the planet, that temperature difference shrinks, and the westerly winds driving the jet stream slow down as a direct result. Slower winds tend to produce bigger, wavier loops in the jet stream's path, loops that extend further north and further south than a faster, more disciplined jet stream normally would. Those larger waves carry a critical side effect that connects directly back to the blocking pattern currently sitting over Europe and North America. Bigger, wavier loops in the jet stream move eastward far more slowly than a tighter, faster-flowing jet stream would, and a wave that barely moves is functionally very close to a full blocking pattern. This is the mechanism researchers increasingly point to when trying to explain why extreme weather events, from prolonged heat waves to lingering cold snaps, seem to be sticking around longer than they used to in recent decades. It is worth being clear about where the science stands on this connection, since not every researcher agrees on how strong the link actually is. Some detailed studies examining specific historic blocking events, including the unprecedented summer of 2018 over Northern Europe, found no clear evidence tying that particular event to a human-driven trend in blocking frequency, even though the event itself was statistically extreme and rare within climate model simulations. That kind of scientific caution matters, because it shows researchers are not simply assuming every blocking event is caused by climate change without solid evidence behind that claim. What researchers broadly agree on is that the underlying mechanism, a warming Arctic narrowing the temperature gradient that powers the jet stream, is real and measurable, even if pinning down exactly how much it changes. Blocking frequency in any single event remains genuinely difficult. Combine that slower moving, wavier structural backdrop with a powerful El Nino actively pushing a high pressure anomaly into place over the Northern Hemisphere right now, and you get a pattern prime to stick around far longer than a typical passing weather system would. The practical consequences of this particular block are already showing up in seasonal forecasts. Analysts tracking the pattern say the blocking high anomaly over northern and north-central Europe looks set to grip the continent's weather pattern through the fall and potentially into winter, while similar high-pressure ridging is expected to lock in warmer-than-average conditions across the south-central United States, the central and northern plains, and southern Canada. A pattern that gets stuck in place for months rather than days does not just mean a few extra hot afternoons, it means entire seasons. A below-normal rainfall stacking up in already dry regions, an elevated heat risk persisting across areas that would normally get relief from a passing storm system every week or two. For anyone trying to make sense of why this summer's weather has felt so relentless, this is the underlying story connecting so many of the individual headlines together. It is not simply that any one region is having an unusually hot week. It is that the atmospheric mechanism responsible for moving weather along and giving regions a break has, in a very real and measurable sense, gotten stuck, and the forces currently reinforcing that stuck pattern show little sign of releasing their grip anytime soon. If you want to understand exactly how this pattern continues to evolve in the weeks ahead, make sure you are subscribed to this channel so you never miss an update. This is one of the more important atmospheric stories shaping weather across 2 entire continents right now, and we will keep breaking down exactly what the data means as it develops. Thanks for watching, and we will see you in the next one. That kind of reshaping happens because the tropical Pacific plays an outsized role in steering global atmospheric circulation, functioning almost like a thermostat for weather patterns thousands of miles away. When ocean temperatures shift as dramatically as they do during a powerful El Nino event, the atmosphere above responds by adjusting where its major high and low pressure systems tend to sit, and those adjustments cascade outward across entire hemispheres. This is precisely why forecasters, watching a strengthening El Nino this year, are paying such close attention to blocking signals showing up not just in the Pacific, but thousands of miles away over Europe and North America as well. If you are finding this explanation genuinely useful, take a second and hit that like button right now. It helps this channel keep bringing you research-backed breakdowns like this one straight from the atmospheric science itself. But El Nino is not the only force scientists believe is reshaping how often and how powerfully these blocks form. There's a second, slower moving factor at work, one tied directly to how quickly the Arctic itself is changing. The Arctic Council has highlighted research showing that the Arctic is now warming roughly 3 times faster than the global average, and that accelerated warming is quietly reshaping the entire structure of the jet stream itself. If you want to understand exactly how this pattern continues to evolve in the weeks ahead, make sure you are subscribed to this channel so you never miss an update. This is one of the more important atmospheric stories shaping weather across 2 entire continents right now, and we will keep breaking down exactly what the data means as it develops. Thanks for watching, and we will see you in the next one.